in this section we will finally introduce differentials and derivatives of maps between Rn and Rm, or between their subsets respectively. So I've taught you now multiple times that differentiation can be seen as linear approximation. And this was something I had in Mathematics 1 in the following theorem. This is just from the lecture notes from Mathematics 1, Theorem 4.6. There we've seen that if we have a function on an interval going to R, this is just the shorthand version here of that theorem, and we have a point in the interval, then f is differentiable in that point if and only if there is a certain value which we call f prime of a, such that the following holds: f of a plus h is the same. So the idea is now that h is something small, so we're somehow close to a, or in our new terminology, in the neighborhood of a. That a plus, if we go a little bit away from a, this is the same as f of a plus this value f prime of a times h plus phi of h, and this should be read as f of a plus a constant times h plus stuff, something small. And something small just means that this satisfies this condition here. The limit as h goes to 0 of phi of h divided by the absolute value of h is 0, meaning this goes faster to 0 than just taking the absolute value of h. So this is basically something, something negligible. So this means we have some constant value, and this here, if we view this as an expression in h, this is multiplication with a constant. And by our new knowledge about linear algebra, this is a linear map. So we could also rewrite this as f of a plus h is f of a plus a of h plus phi of h. So where a is now a map from R to R, a of h is f prime of a times h. This is just multiplication with a number. And we know that a is not just any map from R to R. We have seen that multiplication with a constant is just the same as multiplication with a 1 by 1 matrix, to be very fancy. This is a linear map from R to R. So this is the way we can see this. It's differentiable if and only if we can find a linear map, and we have seen, so this follows indirectly from what we've learned about linear maps and matrices, that all linear maps from R to R are of this form, multiplication with some fixed number. This is all linear maps. So this means that f is differentiable in A if and only if we can find some linear map such that f of a plus h, so for values close to the parameter a here, we have that it deviates from f of a by just something which is linear in h plus rubbish. So plus something very small which is not that important. So this means multiplication with f prime of a is the best approximation of f by a linear map in a neighborhood of a, so close to a, right? And so, I mean, the picture is very simple. So if we have some graph like this could be the exponential function or something, and we have some value a, then a linear function, or to be precise, an affine linear function would have a graph which is just a line, and this line would be tangent to the graph of the function here. So the slope here, this ratio would be f prime of a. So this is what we do. So this is the best approximation by a line, by a linear map. And this is now the philosophy for which we can now use our, maybe these axes look so naked. Sorry, I can't just leave them unlabeled. Sorry about that. Now, we have learned so much about linear maps and about linear algebra that we can now make use of this and to generalize the concept in precisely this direction, that we demand this to be, demand a linear map to be there. Because if you take a look at this, this construction here now, except for this condition that h, there is an absolute value of h included, this here can be precisely written down in the same way if we have a map from Rn to Rm. We just need to specify the condition for phi here slightly differently. And the idea is, if we are in Rn or Rm or whatever, we can replace the absolute value by simply the norm. So let's generalize this condition by doing precisely the same thing, but taking linear maps between arbitrary Rn and Rm, and by taking a map phi where this condition holds with norm replaced, with absolute value replaced by the Euclidean norm. Okay, so this is what we will do. And this, now without further ado, let us do the definition. Let me just start right here because it's so important and I want to have enough space. So definition 12.10. So we have M and N in N. We again have an open subset of Rn. And we have a map from U to Rm. So A, and again, so this is now a replacement for an interval, so an open set where we have some points nearby. Because if we want to generalize this, of course, we need to do this for values of h, and we need to ensure that if h is sufficiently small, so if we're so close to A, this is really well defined. So f of this is defined, and this means, again, this openness condition comes in, so we need a little space around A, so a little epsilon ball in which we can just move around, and such that we can formulate these conditions there. Now, so let A be a fixed point in U. Then F is called differentiable in A. If, and now we go the way I mentioned, if there exists a linear map, so linear is here the important word, a linear map, which I will again call A. I hope this is not confusing with respect to matrices, but now it's a linear map, which is almost the same as a matrix in this case. So a linear map from Rn to Rm, such that the following holds, such that f of A plus h, we have to specify now which in which set h may lie, but anyway, f of A plus h is f of A plus A of h, so the linear map applied to h, plus rubbish, plus phi of h, where for all h in a set I call U prime, where U prime is the set of all h in Rn which are sufficiently small, and by this I mean such that A plus h still lies in U. And what could now show, I haven't done the details about this, but you could show at this point that this is again an open subset of Rn, but this shall not bother us at the moment. So where U prime is this, and where phi, I have to now specify what phi does. Phi goes from U prime to Rm, where this and this map phi satisfies now that it's also kind of going to zero fast, and by going to zero fast, I mean now that h is going to 0, and we take 1 over the norm of h times phi of h, to be precise, because phi is going to Rm. This is so multiplication of a vector by a scalar, where this goes to 0. And this is now a limit in Rm, and we have made limits, sense of limits in Rm in the previous chapter, so in that sense we have generalized this as well. So here we just have really taken this precise analog of, or we have this direct analog of the situation for the real functions. So we have found a linear map, and this linear map now, which has this property, this shall be our derivative. So this is the generalization of the derivative, and just to distinguish from the other derivatives we have seen before, we call this the differential. So we then, let me do this here. We then put, and here it's also the case that several notations are used, different books use different notations. My notation will be df, so capital df, with an index a for the point. Of course, this depends on the point. This is now the notation for this particular linear map with respect to A. So as an object, it's a linear map from Rn to Rm. And we call dfa the differential of f in A. Okay, some also call this sometimes the derivative, or the total differential is also sometimes in order in a total derivative as compared to partial derivatives, but I will just call this a differential. I hope this is fine for everyone. And let me just list the other notations that are in use for this map. So other notations, and it now depends on which book or which lecture notes you take a look at. So other notations include, for example, DAF, so putting the A in front, or small d f a, or some even just write f prime of a, but I want to be not to confuse you too much, so I'll use a different notation there. Yeah, did I have any other notation I wanted to mention? Oh yes, and some also called TAF, T for tangent map, but I don't want to elaborate on that. Now, this is all notation for the same, but my notation will be this. Okay, and of course you know what's coming. We call f differentiable if it's differentiable in every point, if f is differentiable in every a in U, and yes, and call. And now, of course, we cannot just find this as before. We had f prime as a function. Now we have to be a bit careful because we can also define df now as a map which depends on the point A. And now this takes a point in U and associates with it the differential. So it goes from U to the space, to the vector space of linear maps from Rn to Rm. And so df as a function with argument A, this is now defined as the differential dfa, and this is then simply called the differential of f. But as you can see, it gets a bit more complicated. Not as before, the differential of a function from an interval is a function of the interval. Here it's again a map from U, but of course the target here is a bit more messy. So this is a vector space, and there is even also a way to put a norm on this and then generalize this and define the differential of the differential and so on. We will go to higher derivatives later on, but so long story short, there is a great deal to do about this and to expand on this, but I will not go into detail here because that should not be relevant for now. Okay, this is just the definition. One remark before we proceed. Namely, this is well defined. The differential of f in A, using the same notation as before, is well defined. So now you might ask, okay, why should it not be? The only thing is here, I'm suggesting that there exists a linear map such that this property holds, but what if there's more than one? Theoretically, I've just defined the fa to be this map, but if there are more than one, this differential would not be well defined because I would have a choice there. The key property is here now, this linear map, the linear map in this definition, so in definition 1210, is unique. So there is really exactly one such map. Proof of this is a bit tedious and very technical, and I will spare you from that proof, but have included a proof in the lecture notes. So just take yourself a quiet moment and try to digest that. So it's a bit, yeah, this is just a long computation and not very interesting. Okay, we've now got differentiability. So we've seen differential is unique and well defined. Okay. And we will compute derivatives, differentials later on. I ask you for a bit of patience because I want to establish a bit more theory and we need a little more techniques to compute such maps. Because of course, if you just see this purely this definition, there's no obvious way of computing this map A. So why should there be? And so to do this, we just need to establish some properties of the differential, and then we will see step by step that this is not that hard to compute this once we know a bit about its properties. Okay, first of all, Theorem 1212, and this is now a straightforward analog of the corresponding property for differentiable functions. For differentiable functions on intervals, as we had in mathematics 1. So if we have m and n and n, u in Rn open, f from u to Rm, and a in u, then if f is differentiable in A, then f is continuous in A. Here we go. So we've seen, I've mentioned in the previous section that there are partially differentiable functions which are not continuous in that point, which is really awkward. Here we now the world is back intact again. So everything falls into place. So again, we see differentiability implies continuity as it should be from our intuition. Okay, this holds true, and this I want to prove here. Now this, maybe I need to erase already, or let me try the first steps. So I want to do this by using sequential continuity. So use theorem 1130 about sequential continuity. So we will show that it's sequentially continuous, so to say. So if I take a sequence converging to A, the values of f will converge to f of A. So sequential continuity. Okay, let xn, n in n, be a sequence in U with limit A. So the limit of xn is A. So we need to check what do the values of f do. And to do this, we just basically need this equation and to exploit its properties. And so now we have a sequence going to A, but if we were to write this in this fashion, we just introduce another sequence of points. Namely, we put hn to be xn minus A. So in other words, xn is A plus hn for every n, and this is what we had in the left-hand side of the definition there. Then I will erase first because I need more space. Let me erase this. The sequence hn that we just constructed obviously satisfies limit as n goes to infinity, hn is 0. Now, if we want to use the definition of the differential and the defining equation for this, we have to insert these hn into the differential. And we know already the differential is a linear map from Rn to Rm. So by corollary, what was the number? That was in chapter 11. 1142. 1142. The differential as a linear map from Rn to Rm is continuous. But then, by sequential continuity applied to this linear map, it follows that the limit as n goes to infinity of dfa of hn must be dfa of 0. But as we know, it's a linear map, and linear maps at 0 are always 0. So we know this expression tends to 0. And now if the map phi is given as in the definition of differentiability, so that we have this equation, the definition of dfa, then it also holds that phi of h divided by the norm of h goes to 0. And the necessary condition for this is that phi itself goes to 0 if h goes to 0, which particularly means that the limit as n goes to infinity of phi of hn is 0. So this means the limit as n goes to infinity of f of xn, this is now by definition the limit as n goes to infinity of f of a plus hn. And this is now by definition of, if we now insert the defining equation of the differential, this is the limit as n goes to infinity of f of h, which is obviously independent of n, plus dfa of hn plus phi of hn. And if we take a look at this, I mean limits and sums commute there. This is what we've seen for general norm vector spaces. So this is just f of a, and we've seen this goes to 0 and this goes to 0. So all that remains is f of a. So the limit of the f of xn is f of a, and since xn was chosen arbitrarily, this shows that f is continuous. This is sequential continuity. Okay, so this is what we've seen. So differentiability implies continuity, and let me just fix that as a remark. 12, this must be 13 now. This is false, so partially differentiable functions in a point, but I don't write this down exactly. Sorry, maps, so functions are not necessarily continuous. And this is now the map that we've seen in the example I already mentioned. So we have seen the partial derivatives exist, but we have seen in the previous chapter that the function we discussed there was not continuous. So this was example 12.7.2. Okay, this was our counterexample there. Now, another nice property of the differential, and this is also something I want to omit the proof of because it's a bit tedious. So, theorem 1214, namely, again, m and n in n, u as a subset of Rn is open, f maps from u to Rm, and now the question is, we can again study the component functions. So what follows about the differentiability of the component functions? So if we write f as f1 to fm, where fi maps from u to r for all I in 1 to m, and assume we have some point a in u, then so, of course, we would like now the differential to behave well, and the good news is it does. So, f is differentiable in A if and only if fi is differentiable. Differentiable in A for all I. Okay, and if we have differentiability, then also differentials behave well. So in that case, the differential df, so dfa evaluated at some vector v in Rn, this is the same as just taking component-wise differentials. So df1 of a. Now, if we have a collision of indices here, we just usually put parentheses around this whole df something and put this as an index next to it so there's no confusion. So this differential of f1 in the point A evaluated at v and until dfm in A evaluated at v for all v in Rn. Okay, so this is good. This is we can do, they behave what we expect them to behave, so differentials behave nicely, and so this especially tells us if we know how to derive functions from u to r, we can also derive everything from u to Rn just component-wise again. So the proof again is in the lecture notes. Okay, now the crucial question now. We have seen partial and directional derivatives in the previous section, which was the kind of naive notion of how to differentiate a function by just restricting to the curves. And here we've seen the big thing, so the big differential which kind of studies the function as a whole. And now, of course, it's kind of nagging at us why or shouldn't they be somehow connected? Because before, I mean, this is all a notion of derivatives, so this is the one that should be the right one, so the previous one, what about that? What do directional and partial derivatives do? And the good news is there's a wonderful connection between them, which I will also prove in detail because this is really interesting to see. Theorem 1215. So, same setting, m and in n, u in Rn, an open subset, and f from U to Rm. And this shall be differentiable in a certain point A in U. Okay, so what happens if it's differentiable? What about directional and partial derivatives? And it follows that then all directional derivatives of f exist in this point. Okay, this is good news. This is great. Wow, the old notion now really exists there. So this supersedes everything. So the big differentiability implies that we have all the directional derivatives. And not only that, and the differential at the point A, evaluated in some vector v, is the same as the directional derivative of f in that point A. Ah, that's nice. So this is another explanation of why the derivative sees more. So this is true for all v in Rn without 0. So instead of just taking isolated directional derivatives, so looking at them individually, this is the map which contains all directional derivatives here all at once. So you can see that this is kind of superpowers because we have all the directional derivatives in there. So everything encoded in one big map. So this is something, this is kind of one of the most beautiful equations, I think, of this chapter here, or of this whole lecture. So here you can see really there's a direct connection between the directional derivatives and so on. And the good news is, this helps us really in determining differentials because, as I said before, by this defining equation, it's hard to compute differentials. There's no obvious way, but we have seen how to compute directional derivatives. We can just either do a differential quotient by hand, or in case of partial derivatives, we can just compute the partial derivatives explicitly, and we will see a bit more about that, what this gives us for the differential. But this is the key equation for computing the differential and the values there. Now, of course, we need to see why on earth this should be the case. And turns out this is actually not that hard. So we take a particular direction, so we assume it's differentiable, and we need to check what the directional derivatives do. So we take a direction v in Rn without 0. And gv is now the corresponding map which we need to derive to get the directional derivative there, namely dv from minus epsilon to Rm. I don't write this down this time, but epsilon is just sufficiently small, and as I said, from the openness it follows there is such an epsilon, blah blah blah. But we can find an epsilon such that this map gv from minus epsilon to Rm, which is gv of t is f of a plus t times v. So this map, the directional derivative, is formally defined as the derivative of this at 0. So what does this mean? If we now insert so let me just write for suitable epsilon bigger than 0. Then, if we take a look at the quotients which define the derivatives here, then for t element minus epsilon, we just see the following. So, without 0, we take a look at the corresponding quotients. So the derivative of this as a curve is the limit of 1 over t of gv of t minus gv of 0. Okay, the limit of this as t goes to 0 is the directional derivative. Now, let's write in these definitions. So this is 1 over t of f of a plus t v minus f of a. Now, since f is differentiable, in A, there exists some map phi from u prime, which I won't define this time, but this is the set analogous as before, with limit h going to 0 of phi of h divided by norm, 1 over the norm of h times phi of h, scalar times vector, so that this is 0. Oops. So there exists a map such that f of a plus h minus equals f of a plus dfa of h plus phi of h. And if we now use this argument, sorry, there's a mistake. If we insert this into that equation, we get, so if we that h to be t times v, this means we get that 1 over t gv of t minus gv of 0. So there we have f of a plus tv minus f of a, and if we just subtract here f of a on both sides, we get that this is the same as 1 over t times dfa in t times v plus phi of tv. Okay. Now, dfa is a linear map. Here we have a scalar inside, so by linearity we can just move this outside. So dfa is linear. This means this is 1 over t of t times dfa of v plus phi of tv. Yes. Okay, and then we of course see in the first summand everything, the two t's cancel each other out. So this is the same as dfa of v plus 1 over t times phi of tv. Okay, now this already looks a lot like a derivative, and we just have to show that this is basically something small, something rubbish which vanishes. And we know that phi has a similar property, but we just have to figure out a bit about the details. And so if we take the limit as t goes to 0, this means on the left-hand side we get dv of f of a. So the limit as t goes to 0 of gv of t minus gv of 0 divided by t. So this is now by our formulation the same as taking the limit here as t goes to 0, and since this is continuous, we get this is dfa of v plus the limit as t goes to 0 of 1 over t phi of tv. Okay, so we're almost there. We have dv of f of a is the thing we want plus something something we don't want. So we just need to show that this limit here is indeed 0. And for this we do the computation. We compute. So to show that this goes to 0, this is a vector in Rm, we know that by properties of the norm, it suffices to show that the norm goes to 0. Just by, the norm is 0 if and only if the vector is 0. So we need to show, or it suffices to show that this limit here goes to 0. So 1 over t times phi of tv. Okay, and now we play around with this a bit. This is some positive factor, so we can not necessarily, we can pull this out with the absolute value and then move this in. And this means this is the same as t goes to 0 of the norm of phi of tv divided by the absolute value of t. This is now we really have a number here, so a real number in the numerator, so this works. Now we're almost there because we have a similar property of phi, but so here we need to somehow divide by the norm of the argument, so by tv. But this is a nice little game because this is the limit as t goes to 0 of phi of tv divided by the absolute value of t times the norm of v, and now multiply everything by the norm of v. This is just for the limit, this is just some constant, and this here by the properties of the norm is the same as the norm of tv. So this is the same as the limit as t goes to 0 of the norm of phi of tv divided by the norm of tv. But this in turn is the same as the limit t goes to 0 of the norm of 1 over the norm of tv of phi of tv. Okay, and now we know this is now by the defining property of phi. If the argument goes to 0, this expression here goes to 0. And if t goes to 0, obviously the argument goes to 0. So this is really 0. So this means this goes to 0. And so the norm of this goes to 0. So it follows that the limit as t goes to 0 of 1 over t phi of t v is 0. And this shows the claim. So this shows the directional derivative of f in A is just v inserted into the differential. And this is what we wanted to show. Sorry for squeezing here. So this was a bit technical, so we can probably forget about that, but we can see from the definition of the differential that if we insert this here, it just satisfies precisely the nice relation here, so we can really kind of use this differential quotient and instead see that this is that we can insert a differential at that point. Okay, after erasing, we will then discuss some more properties and also see some examples of derivatives now, because this now really helps us in computing. And so we will see some ideas, and we will also specify it a bit, because we have seen now if the map is differentiable, then the directional derivatives exist and we can compute them. But we haven't discussed the other implication. We haven't discussed if we now have a map and all directional derivatives exist, if we have this at the point, is it then differentiable? And the answer turns out is no. There can be strange things happening, and this is what we will see after erasing here. The previous theorem shows in particular that if a map is differentiable at a point, then all partial derivatives exist at the point, because you can compute them by the differential. So in particular, if a map is differentiable at a point, it is partially differentiable. This is an implication that always holds. We will kind of summarize this with a few other facts in the end of the section. So a differential map is partially differentiable. What about the converse? Of course, we wouldn't need two notions if it was equivalent. So the converse indeed does not hold. There are examples of partially differentiable functions which are not, or maps which are not differentiable. And I will show you two of these in this example. Namely, the first one is one we already had on the board in this section, or was it? No, in the previous section. This interesting function here, which is defined either for non-zero points, we have this expression, and in 0 it's just 0. So we've seen about this, that this is indeed partially differentiable in 0, 0. Namely, we have seen f is partially differentiable in 0, 0. We've computed the partial derivatives in 0, 0. But we have also seen, this was an example that not all directional derivatives need to exist. And we have seen here in particular, this is what we've computed explicitly, that the directional derivative, if we insert the vector 1, 1 as a direction here, f does not, in 0, 0 does not exist. So the previous theorem implies it cannot be differentiable, because then this must exist. So f is not differentiable. In A. Okay, so this is our first example of a map which is partially differentiable but not differentiable. And now you might think, okay, the problem here is that there is a directional derivative that does not exist. But what if there are all directional derivatives existing, and if this really, if they all exist, do we then already know it's differentiable? And unfortunately, the answer is still no. This is still not enough, and we will see an example of this now. So we again consider a function from R2 to R to keep things rather simple. And we again define this by some rational function there, namely f of x1, x2 is supposed to be either x1 to the power of 3 divided by x1 squared plus x2 squared, or 0. And here, if the point is non-zero, and 0 if the point is, it's not the origin, so to be precise, 0, 0. And we put the function to be 0 if we are in the origin. Okay, so another function which is kind of, where it's non-obvious which properties this has. So I first claim that all directional derivatives exist in 0, 0. So all directional derivatives exist in 0, 0. Okay, and this is what I will prove. So take some arbitrary directions, so let V be a vector with entries v1, v2 in R2, which is non-zero. Then, for all parameters t non-equal to 0, we take a look at the following quotient. So this is a function, so we can write everything as a quotient. So we need to discuss f of a plus t, of 0, 0 plus t times v minus f of 0, 0 divided by t. And for this, the limit of t going to 0 gives the directional derivative. So let's first do the computation without the limit for a fixed choice of t. So let us compute. F of 0, 0 is 0, so this doesn't matter. And this is just f of, this is t times v, so we have, and this is 0 here before, so we have t times v, which is t v1, t v2 divided by t. And this is something we can obviously compute because the function is explicitly given. So this is 1 over t, let's put this here in front, times, and now t, so x1 is t v1, so in the numerator we have t to the 3 x1 to the 3 divided by, and there we have x1 squared, so t v1 squared, which gives t squared v1 squared, plus now the second component t squared v2 squared. Okay, and if we take a closer look at this, so we see that here we have t3 in the numerator, and here we can take out the t squared, and we have another t here in the denominator, so we have t to the 3 in the denominator as well. So this can be reduced to, so we can reduce this, 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 and this, and so all that remains is, oh sorry, not x1, v1. All that remains is v1 to the 3 to v1 squared plus v2 squared. So, for the directional derivative, this means we have already found our expression. So, dvf in 0, 0, this is by definition the limit as t goes to 0 of this expression here. So, f of 0, 0 plus t v minus f of 0, 0 divided by t. So, by our little computation, this is the limit as t goes to 0 of this expression. v1 to the 3 v1 squared plus v2 squared, and obviously there is no t included in there anymore. So this is just constant, so the result is v1 3 divided by v1 squared plus v2 squared. So indeed, all directional derivatives exist. We have chosen an arbitrary direction vector here and have this as an explicit formula for the directional derivative. Okay, so I had said before that this is not differentiable. So the question is, what can go wrong? Now, there's an easy observation. So, if f was differentiable in 0, 0, then just by this previous theorem, by 1215, we have df in 0, 0 of v must be the directional derivative dvf in 0, 0 for all v in R2, which is non-zero. But then we need to have a certain property, namely, it's not enough that it exists, but we know that this map here, df 0, 0, is a linear map. So what does this mean for directional derivatives? Then, in particular, we make the following observation. Let's take the directional derivative of v plus w for some vectors v and w. An f of 0, 0. So if we add two vectors here and take the directional derivative by the sum, this is then df 0, 0 of v plus w. And since this is a linear map, we now get that this is, so by the linearity of df 0, 0, this is df 0, 0 of v plus df 0, 0 of w. But these are again, directional derivatives by just using the same equation in reverse. So we get, let me write this on the next blackboard. So then follows that the directional derivative in direction v plus wf of 0, 0 must be the same as dvf of 0, 0 plus dwf of 0, 0. And this for all directions. So for all vw in R2 without 0. Now, this must hold. This is the linearity property in this vector. And we just have to show that this linearity property is violated by this function. So we just need to find some vectors which kind of make a mess here. So here we compute. And it turns out we don't need very complicated vectors. The first one we take is 1, 0. So the directional derivative 1, 0. This is the same as the first partial derivative, of course. Okay, so this just means we need to insert 1, 0 in this, in this expression here. So v1 is 1 and v2 is 0. So we see we get 1 divided by 1 plus 0. So the result is 1. Okay, let's do the same with 0, 1. So, technically with the second partial derivative. Okay, what is this? This is, here v1 is 0, v2 is 1. So here we have 1 in the numerator and 0, 1 in the denominator and 0 in the numerator. So we get 0. Okay, now d1, 1. F of 0, 0, which is now the sum of these two vectors. So let's insert this. So we have both values equal to 1. So we have 1 divided by 1 plus 1, which is 1 over 2. So in particular, we see that the directional derivatives in direction 1, 1, f of 0, 0, is not the same as the sum of these two. And this means, by what I just said, so we have the linearity property if it was differentiable. So it follows that f is not differentiable in 0, 0, because all directional derivative exists, but they don't satisfy the linearity property that's necessary for the differential. So this is where differentiability fails. Now, next step is you might ask, okay, we know that all directional derivatives, having them is not enough. But what if we know that all directional derivatives exist and it is kind of linear in this directional vector? If we have this linearity property, is it then differentiable? And unfortunately, the answer is still no. So this is very technical. I don't want to go into detail there because this is more for those of you who are really interested. So even if f from, let's say, I think we actually create a very simple example in R2. So say if we have a map from R2 to R was partially differentiable in 0, 0, and the following expression, so the map which goes from R2 to R, where with each v we associate the directional derivative in the direction of v. So if this is linear, so that the linearity property that is required is satisfied, f might still not be differentiable. In this point. And since this is really technical thing, I will not give you another example of this because this was already technical enough or explicit enough. I've included one in the lecture notes, but without any computations, just a function where you can check that this is really then not differentiable. So I just indicated a bit of how to show this. Okay, so we see that from the partial derivatives we can not really tell about differentiability here at this point. But we can now use the connection between, so we have before established this connection between the directional derivatives and the differential, and this helps us in formulating an explicit formula which is actually useful to compute differentials. Namely, this is just a corollary where we will need the linearity properties, so a corollary 1217 where we need a little bit of linear algebra but very harmless. Assume we have U as a subset of Rn which is open, and assume that f goes from u to r to the m, where m and n are again some arbitrary natural numbers, which I want right now again this time, and assume that f should be differentiable in a point A in u. Then we can use this formula. Then the differential dfa in some vector v is now the same as, and we can now use partial derivatives, namely it's the sum from 1 to n over the partial derivative of f in the point A times vi, where vi is the ith component of v. So this holds for all v which is v1, v2 to vn in Rn. Okay, this formula might not look very insightful, but the good news is this is something we can compute. The vector is given, this is some given vector that is given to us, and the partial derivatives, we've learned that we can compute them by just using the standard derivation rules for the standard differentiation rules that we learned in Mathematics 1. So this is really standard differentiation, which is of course easier than taking directional derivatives, but these guys we can compute without many difficulties, and v is given, so this is an expression that you can really write down. And just keep in mind, so what's written here, I've actually taken this in the wrong order because this looks more natural to me somehow. This is a real number. And this here, if it's a map to r to the m, the partial derivative is an element of Rm. So here it's again a scalar times a vector. So actually I would have to write this in front, but I will use now the notation that kind of multiplying from the right hand side is meant to be precisely what you think it is, namely just multiplying in the same way, because multiplication is commutative there, it doesn't matter. So this is really the sum of vectors multiplied with scalars, just to check the dimensions here and to get this right. Now, why is this? This is actually really easy to see, because we just need to apply the formula from the previous theorem. Namely, by theorem 1215, we know that df is then gives us the directional derivatives. So in particular, if we insert the canonical basis vector ej for some j, this is nothing but directional derivative by this basis vector, and this is precisely what we call the partial derivative. So this is how we define the partial derivatives. So this is dj or partial jf in the point A for all j between 1 and n. Now, we just need to establish a bit of linear algebra, namely, hence, for all arbitrary vectors, v which are given as v1 to vn, we get the following. dfa of v. Now we can write v in a fancy way, namely as a linear combination of the canonical basis. That's the trick we already used a bit before. So this is just basically the entries of the vector are just the coefficients as a linear combination in terms of the canonical basis. Meaning this is the same as the sum from j equals 1 to n of vj times the jth canonical basis vector ej. Okay, and now we can just use the linearity of this map, because we know then that we have a finite sum here. These are scalars, these are vectors, so we can just use the standard rules or the standard properties of linear maps, or the defining property of linear map actually. Namely, this is now the same as the sum from 1 to n of vj times dfa of ej. So just by linearity, and there we have it already, because this is the partial derivative. So this is the same as the sum from 1 to n of vj times partial j f in A. And just by switching the order of the two factors, and I don't know why I changed the notation from I to j in the index, but this doesn't matter. This just shows the equation. So we just need linearity there, and our knowledge of linear algebra here really helps us that it's just sufficient here to compute the partial derivatives and multiply them in a nice way with a vector. So if we know differentiability, all we need to know is the partial derivatives, or all we need to know to explicitly compute is the partial derivatives, and then we get everything by this formula. We will see examples of this later on. Okay, now there's an obvious problem, because now we see, okay, if the map is differentiable, we have a nice way of computing this, and we have learned kind of how to use the previous techniques for the partial derivatives and so on, but we still don't know how to find out if a map is differentiable. So far we just have the definition, and you see from the definition it can be pretty dull. So how should we find a linear map which has this property? This is for easy examples, this is actually doable, but for anything which is a bit more complicated, this is horrible, and this is really not, this is something not very good. And so what we would need is now a better criterion. Oh, I forgot the QED box, I'm sorry to, this gives satisfaction, okay. We still don't know how to find out how to show that a map is differentiable without having this tedious computation with linear maps and so on. So this is still missing. But it turns out there is a good criterion which already gives us differentiability. And the good news is we just need to compute the partial derivatives for that. And from the partial derivatives, the existence is not enough, but we need one more little more property, and then we can already follow or conclude that the map is differentiable, which will be kind of our main criterion of showing that something is differentiable, which we will use like 99% of the time probably. Maybe a bit exaggerated, but this is kind of what's mostly used for this. Okay, let me erase and then we'll discuss that.